test, exam. All right. Calculator, laser pointer, 9 a.m. Well, good morning. Any questions about the labs? Please. Oh, of course. How could I forget? Question is, are these two problems the same? Yes. No. I don't want to know. It's about a radioactive decay. That's my last attempt to get 100% correct answers. Don't miss this chance. Survey says. They should add physics questions to Jeopardy. One student doesn't like me. All right, so what's happening here? We always begin from 100% of something. So if we want to sketch a graph, we start from 100%, and the number of radioactive elements, the mass of radioactive element decreases. And 2 means it stops here at 20%. And if we start from 100 and decrease by 20, we stop at 80%. That's the reason they are different. But also it means we have to solve them differently, of course. We can use the same equation for both, the law of radioactive decay. And if we don't see anything related to a half-life, there is no word half, yeah, we should use the general equation. We haven't used it yet, so that's going to be the first example. That's how it looks in general. And now we just have to write 20% of initial value, which is 100%, times the decay constant, well, exponent to decay constant, and 5 hours. You can cancel percent, of course. And that gives 0.2 is equal to this. Why do minuses? Two minuses. Just you didn't see it. So this is an exponential equation which has to be solved, and any equation is solved in general by the same approach. We have to figure out how to isolate an unknown. In this situation, an unknown, the lifetime is directly related to the decay constant, and if we find decay constant, we can calculate the lifetime. Well, so what do we have to do? We have to undo what something else is doing on the unknown. So in this situation, what could have been done? We could have taken a square root of both. The rule says whatever we're doing to one side, we have to do to another side. Yes?
So for this equation, it doesn't matter if the t is an hour?
We always can make a conversion. We can do it right at the beginning or right at the end if we want to. At this point, we just keep in mind those are hours. And if I do all calculations in the end, I get hours, but I can convert hours into seconds now or later. So of course, taking a square root wouldn't help. So we can take an inverse sign of each. Wouldn't help. So we have to keep going until there is a function found which would undo the exponent. What function does that? Exactly. So etc., etc., etc. We need to apply the natural log to both sides. And well, from here we can continue. Natural log of 0.2 should be equal to natural log of this. And the good thing about this, again, according to the definition of this number, the natural log of e equals 1. So these two symbols just cancel out each other, like sine and inverse sine, square and square root. So the natural logarithm of 2 will be equal to negative 1 times decay constant times 5 hours. Now we have to take a calculator and calculate the natural log of 0.2. Good thing it's a negative number. Negative 1.61 equals negative, because the decay constant has to be positive, so we need to have a negative and a negative to cancel it out. Well, 1 over lambda, which is technically what we are looking for, lifetime, will be equal to 5 over 1.61 3.1 hours. So if we start from 100%, so we wait about 3 hours to get to about 1/3, yeah, because that's what half-life lifetimes indicates, to about one third of that, about 33% left. But still we have to wait a couple of more hours to get to 20% left lifetime, and this is 5 hours. That's it. And of course we know what to do to solve the second problem. We just have to know that if increased by, or decreased, well, decreased by means the difference. That's going to be equal to 100% minus 20%, and that's going to give us the final value. And now we just have to repeat the whole procedure. Yeah, we start from 100%, but now we add 80%, and well, 80 is equal to 100 times E. And now we just have to change the number from 0.2 to 0.8. The natural log of 0.8 should be equal to this. And half-life, which is 1 over lambda, will be equal to negative 5 over the natural logarithm. It makes it positive, of course. $22, well, 0.4. So it's all about one word, by, yeah, or two. The mathematics is exactly the same. Question. So, carbon-14 is being used to date materials, archaeological dig, for example, unearth the bone, and they can measure the activity. And the idea behind carbon dating is that all living things, objects, breathe. Plants, animals, they use breathing to survive, to live, and while doing that, they absorb a certain amount of, well, everything, including carbon-14, which a radioactive isotope. And if now we measure a certain activity from this old sample, we can, well, this is what? Piece of wood. Okay, so we can go to the forest and find exactly the same piece of wood, cut it off, and measure activity. And we make an assumption that this old piece of wood, when it was alive years ago, had exactly the same activity as this fresh piece of wood has now. So in this case, we can measure two values: activity now and activity which would have been thousands of years ago. And here, what we have is we have the old piece of wood, and activity, this R, is 0.22 becquerel decays per second. And today, you'll see how it's done, how it's measured. And now we go to the forest and we find exactly identical piece of wood, same size, same wood, everything is the same. And we measure activity, and that is 0.88 BQ. So if we want to relate, if we want to use the law of radioactive decay, we have to know two numbers. So we have to relate these two numbers with these two variables, which would represent the initial, which would represent the final value. What do you think? Is this initial for the law, or this is the initial for the law? What do you think? What do you think?
Probably the bigger one.
The bigger one, because it always goes down. That's it. So, but that is not activity. Technically, this is n, but we can make it activity by multiplying by decay constant. So we should say this is the initial activity, and this is activity after a certain period of time. And because n, the number of radioactive nuclei decreases, so activity decreases with exactly the same law. This is one form of this law. This is another form of the same law. So we start from 0.88. We wait exactly one half-life. If we start from 0.88 and we wait one half-life, what will be the next activity? Why? Because of a definition of half-life, we have to wait until it is a half of the initial 0.44. Is it 0.22? Not yet. So we have to wait one more half-life, right? And that's going to be 1/2 of 0.44, 0.22. So this number n, which tells us the number of half-lives passed, is 2. And naturally, we could solve it from equation. We have to do 2 to the nth is equal to 0.88 over 0.22, which is 4, which is 2 squared. So, of course, algebra and just common sense agree with each other. So we have to wait 2 half-lives. But we know that each half-life for carbon-14 is about 6,000 years, 5, 7, 30. So how old is the sample? Well, it is 2 half-lives old. That's it. That's it. Multiplication. That's not a... 2 times 5730. 1146, or about 12,000 years. So this is just an explanation. You have the answer, and there's a link if you want to read more about carbon dating. Question. Again, it's the same piece of wood. We just measured activity of it. But what can we say about its mass? Right now, because we just dug it up, we place it on scale and we read 400. And we are asking, well, thousands of years ago, what was the mass of this piece of wood? So, I'm not going to check. Just let's vote. If you think it was 100 grams, please raise your hand. If you think it was 200 grams, please raise your hand. 300 grams. 400 grams. You didn't raise your hand at all. What is your number? Oh, both of you didn't raise your hand. It's not about thinking, it's about having a specific knowledge. And specific knowledge, it says, if you have a piece of wood and you have radioactive atoms, over time, what is happening? Well, they turn into different type of atoms, they decay, so they're not red anymore, well, most of them, but they remain inside. So, the mass of the sample does change not. The mass of radioactive material inside changes, decreases, but the whole sample is keeping the same mass. And we know that because we talked about it. We had a slide. That slide told us the difference between the mass of the sample and the mass of radioactive material. And just a picture when a radioactive decay happens, change happens, but everything remains inside. New particles created after the decay happened, they remain inside. Now, what do we have? 75% decayed. So what does it mean? Can we write an equation? 75% is equal to 100% times 2, well, divided 2 to the nth. What do you say? I don't even have to walk, right? It's wrong. What is wrong? 75 is wrong. How do we fix it? Well, if 75 decayed, and we have to use the amount which still is in there, remain. So this is our equation, 100%. So this should be equal to 100 over 25, which is 4, which is 2 squared. So again, it's basically the same situation. But there is an additional question about the actual activity. So if now we measure activity, we have a device for doing that. Now, what does it mean? Which one? The one which is final, which is supposed to be related to the initial divided by this. So if now the activity is 10 to the 9th, the initial activity was equal to this number, 4 times 10 to the 9th. BQ, decays per second. Even the mass wasn't changed, right? So now you read it. How many of those atoms responsible for this type of activity, for this amount of activity? Well, activity is directly related to the decay constant and the number of atoms. So this is the activity. We need to divide it by decay constant to get this number. How do we get the decay constant? Well, the decay constant is related to lifetime. So lifetime times 4 times 10 to the 9th. Is lifetime the same as half-life? No. Lifetime actually is longer. It's half-time over natural log of 2, which is 0.67. So now, the thing is that this is what I want to write. When we use BQ, becquerel, that implies using seconds, international system of units. But half-life is in years, so we cannot use mismatched units, so we have to convert years into seconds. 1 year is about 365.25 days, or you can Google, of course. 1 day is equal to 24 hours. 1 hour is equal to 3,600 seconds. And that's going to be the answer. So, units. Yes? No, I'm not sure what you're asking about. If you relate, so the relationship says T1 half equals natural log of 2 times T life, which is natural log of 2 divided by lambda Well, so what is the total mass? Those atoms, radioactive atoms, of course, have some mass. What do we have to do? Well, we know the number. The number of those radioactive atoms is about 10 to the 21st, which was calculated. But if I want to calculate the mass, what do I have to do? Chemistry. I need to know the atomic mass and multiply by the number of atoms. So this is carbon-14. The atomic mass for carbon-14. Well, we can look it up, but it should be practically equal to 14 atomic mass units. That's what atomic mass number tells us. So what do we have to do? 14. We can use atomic mass units, but in this situation I want to see kilograms, so I have to multiply by a conversion factor times the number of atoms. That will be kilograms. Chemistry. Oops. And the answer is here. So it's micrograms. We have a large sample, 400 grams, but only a tiny fraction of that is radioactive, of course. But it's radioactive enough to actually use it for carbon dating. The rest of the sample is regular stuff, wood, regular carbon. That's why the mass remains the same. Even this tiny mass, if they all decay, will not be practically measured. So, another example, what is the activity of a certain sample of uranium-238? Just again, a reminder from chemistry. Activity, R, is equal to the product of two numbers. Now, again, a half-life. So first of all, this is 1 over this. Where is it? Times, oh, I think now I, now I see what you're saying. And, come on. So, N is equal to, what are we looking for? For N, what I found is, my brain thinks it's Friday already. N, no, everything is correct. N is equal to 4 times 10 to the 9th over lambda, which is 4 times 10 to the 9th times lifetime. And that's what I did here. No, everything's right. Good brain. So, because now we are looking for activity, not for N. That's why it's inverted. So, activity equals 1 divided by lifetime times the number. And again, the lifetime is longer than a half-life. So that's going to be natural logarithm of 2 divided by half-life times the number, and the natural logarithm of 2. Half-life, 4.47 times 10 to the 9th. What does the Y mean? Years. Again, 1 year, 365.25 days, 24 hours, 3,600 seconds. Times the number. How many atoms? Well, again, from chemistry, is going to be equal to the total mass divided by atomic mass. And atomic mass is about 238 in atomic mass units. So total mass is 10 kilograms divided by atomic mass 238 at 1 atomic mass unit, because we use kilograms and kilograms, 1.67 times 10 to the negative 27. And that's supposed to be BQ, because we used seconds and kilograms getting cancelled. All we have left is 1 over a second. I'm not going to calculate this number. I just want to demonstrate again the principle. Now, a decay. There are many, many types of decays, but we in physics know 3 most famous, basically, historically: alpha, beta, gamma. And if we have a radioactive sample, we have a photoplate, and we can see it's being exposed. And if we apply magnetic field, we can see that some particles are not being affected, not deflected. Some deflect one way, some deflect another way. And if we use right-hand rule, left-hand rule, we figure out some particles are negative and some particles are positive. And before learning the structure of those particles, people just called them alpha, beta, gamma. So we need to know those definitions. So historically, beta represents an electron or an anti-electron, which also is called a positron. A positive particle which has exactly the same mass as the electron, but if they collide, an electron and a positron, explosion happens, they disappear, they turn into light. Annihilation. So an electron practically has no mass relative to a proton or a nucleus, but negatively charged. This represents a very energetic electromagnetic wave, has no charge, and again, practically no mass. It has some energy, but very low relative to resting energy of alpha particle, for example. Alpha particle has been measured later, represents just a nucleus of helium, a proton, a neutron, and again, each symbol represents the mass and the charge. This is, of course, the approximation. This is an approximation relative to a proton, 2,000 times lighter. And now we can use 2 laws, the law of conservation of charge and the law of conservation of energy, to describe any possible reaction. For example, this is a spontaneous decay. We take uranium-235, place it, weight it, it decays. And we call it the parent particle. Debris called daughter particles. So this parent has 2 daughters, and they only have daughters. And the law of conservation of charge says total charge remains the same. The charge before reaction has to be equal to total charge after. So if you add this charge and that charge, you should get the initial one. And same with the energy, but energy divided by c squared is mass. So atomic mass number before and after should be the same. And that's it. This simple rule describes all possible reactions, just 2 laws. And well, of course, we're going to practice a little. not now. So in this situation, we just get this is summary for one initial parent particle spontaneous radioactive decay. First one, gamma decay, because the law of conservation of charge says charge before and after conserved and mass before and after conserved. So we have the same particle before and after. But it means only initially it was excited in a higher energy state, and then it goes to a lower energy state and emits a highly energetic photon. Beta decay. This is the question. So we have a carbon-14. It decays. We apply magnetic field. We observe electrons traveling after. We know it's an electron. Also, later has been found that there's another particle which called neutrino, but it's so not energetic. It's practically has no mass. We just ignore the presence of it. It exists, but it's not important for any reaction. It doesn't affect the reaction. So what element should be here? What number should be chosen from periodic table for this element? That's the question. And of course, to answer this question, first we need to look up the carbon. What is Z for carbon? 6. We've done it before several times. 6. This is a question mark. So the reaction happened. And before reaction, Z equals 6. And after reaction, total Z equals a question mark plus what? Plus -1. So the question mark will be equal to 6 minus -1, which is 7. What is 7? Nitrogen. That's it. Now, energy says that total atomic mass number before and after should be equal. So 14 before and another question mark plus 0 after. So if this question mark should be equal to 7, this question mark should be equal to 14. This is an isotope of the nitrogen. Done. Now, of course, we have to say something about the energy. What do we know? Well, we know atomic mass for everything, but we need to remember this rule. We've said it before. So if we want to relate the energy before and after, the energy before the reaction. In this case, we have only one element. So it's going to be equal to mc squared, if we use kilograms, or m times 931.5 mega electron volts. This is the question. What kind of a mass is that? Reaction is nuclear. It has to be a nuclear mass, the mass of a nucleus of this isotope of carbon. How do we find it? Well, we know atomic mass, 14.003074. And what do we have to do? To get from atomic mass to a nuclear mass, what do we do? What do we do? Okay. What is larger, a mass of a nucleus or the mass of the whole atom? The mass of the whole atom, because atom also has what? Electrons, and we have to subtract. So we have to subtract 6 electron masses. 0, 0, 0, 5, 4, 8, 5, 8. So this whole number we should multiply by 931.5 to get the initial energy of that system. Now final, or after the reaction. Well, again, we ignore the presence of neutrino, but we have to account for the presence of two elements. Yes? For a nuclear reaction, yes, because it's a nuclear reaction. That's what's happening with the nucleus inside it. It splits, and we get another nucleus plus an electron. So now it's going to be easier, right? Now we know it has to be 931.5, the same coefficient times. Well, first, the mass of a nucleus of the, oh, shoot, I used the wrong mass here. That's supposed to be carbon, and carbon is 0.03241. And then nitrogen, 0.03074. Now, to get the mass of a nucleus, I have to subtract. How many electron masses should I subtract? 7. 7 electron masses. But this is only first part responsible for the nitrogen. We also have to add the energy related to the electron, which is also present. So we have to add one more electron mass. And now we close the parentheses. And if we compare these two numbers, they will not be equal. They will not. Assuming the initial nucleus is at rest, that's all energy it has. But when it splits, those debris actually also travel. They also have kinetic energy. And the difference between these two numbers is that kinetic energy. That's it. I think I have it. So where is it? Oh, okay. I don't have it. But it's mathematics. So this is a general equation for any decay like that. It's called a beta minus decay. It means an electron is a part of a reaction. Now a beta plus. What's the difference is now, instead of an electron, a positron is being ejected, emitted. So it tells us A should be equal to 0 plus A. Yeah. So we know that. We neglect the presence of neutrino. But at the bottom for the charges, Z should be equal to 1 plus question mark. So now this question mark will be equal to Z minus 1. So the element changes, but in opposite direction always in the periodic table. So for example, what will be the result for this reaction? First of all, again, the nitrogen has 7 protons. So the positron has practically no mass, but it's positive. So what should we have for the daughter particle? Well, it should be 6. 13. So this element now 6 is carbon. Carbon. We get a radioactive isotope of carbon, not 12, which is stable, not 14, which is used for carbon dating, another one. Carbon has many, many isotopes. That's it. And I'm not going to do that. You can do it, you know the procedure. I'm just going to write quickly. the energy before reaction should be equal to 931.5 times. For the nitrogen, 13.005738. And I have to subtract 7 electron masses. 7 times 0.00054858. For the energy stored in each particle after, we have to do the same, 30 times. For the carbon, atomic mass 13.003355, but I need to subtract 6 electron masses to get the mass of its nucleus. And now I have to add the mass due to the positron, but the positron is an anti-electron, has the same mass. Close the parentheses. And again, these two numbers are not equal to each other. Some energy is released in the form of kinetic energy. They travel away from each other. And we neglect the presence of this. Well, there is a calculation here. Alpha decay. Alpha decay, what is it? Well, we know that by definition, alpha represents the nucleus of a helium. That's it. So if you want to balance out the reaction, this dotted particle, we can write a helium, it should have a charge by 2 less than initial, and it should have the atomic mass number by 4 less than the initial. And well, this is just one of many famous alpha decays. There's another one. Calculate the energy released per each reaction. Well, that's how a thorium can be made. It's been done. Where does the energy go? Well, the energy goes to, again, kinetic energy. If we start from a resting nucleus, it splits, but those debris, they don't rest. They travel away from each other. They travel away from each other, and actually, they may travel very fast. What can we do about it? Well, this is what we can do about it. Those particles, the debris of the decay, if they travel very fast, and we have a huge amount of those, we can aim those particles, let's say, at water. And they start traveling through water, colliding with H2O molecules. And they transfer kinetic energy. And the water, because its molecules start moving faster and faster, water reaches boiling point and starts boiling, and we have vapor. What can we do with that vapor? We can aim it at a turbine, like a wind, and turbine starts spinning. And we can attach a generator to that turbine and generate electricity. And that is basically an idea for any atomic plant. That's how it works in general. We use that kinetic energy which remains in those particles after decay happened. Now, a different type of reaction happens when we collide something with a stable or unstable nucleus. So in this example, could have been a proton, could have been neutron, could have been alpha particle. So we shoot particles at nuclei, and they collide, get excited, more energy, gets unstable, and then decays, splits. This is what we call the induced reaction. But for any reaction, spontaneous or induced, we still can use two laws: the law of conservation of charge, the law of conservation of energy. So for example, we have three induced reactions here. Neutron induces the reaction with the boron. As the result, we observe alpha particle traveling away, but there has to be something else. What? Well, the law of conservation of charge says that this charge, total charge, 0 plus 5, should be equal to total charge question mark plus 2. This question mark should be 3. This total mass, 1 plus 10, 11, should be equal to this. So that should be 7. Now 3 is lithium. We can add that element. Now, gamma rays, they don't have any numbers, so it doesn't change this. So 12, and that means this should be 11, and this is 25. That means this should be 24. 11 is, you can see it, copper. Well, and same here, that is 0, that is 0. So 1 plus 6, 7, 1 plus 13, 14. That's a nitrogen. Oh, 11. Oh, it's 29. Where is 11? What's this? Good thing I have answers. So, one of the most famous induced nuclear reactions, that's how initially plutonium was made a fuel for first atomic plants. What's happening? Well, we shoot a neutron, the nucleus gets excited, decays much faster, and actually there is a chain of changes. So we call it a chain reaction, and this is a different chain reaction which happens much more faster. And what we see here is a reaction which is used in atomic bomb, in atomic plant, because every reaction also releases some extra neutrons. And those neutrons might collide with the next nucleus, excite it, and that extra nucleus decays and releases extra neutrons. And it happens very quickly if we don't manage the number of neutrons. So, first, I want to show you a couple of things from the past. So, to measure activity, we use a special device, we call it Geiger counter. So, normally, there is always a radioactive background everywhere because cosmic particles and some radioactive materials always around, That results in mutations, good mutations, bad mutations. When a very highly energetic particle travels through this, it excites electric current, and we can hear it or read the number decays per second. Well, in this situation, particles traveling through this. And we can hear that intensity is much higher now. Well, this is uranium-based paint. It looks nice, orange. That's why people used uranium and used to eat from that and used to die after that. Because it's uranium. Well, what can you do? People didn't know a lot about radioactivity at the time, and the people in physics who did all that study, they just put it in a pocket and walk with uranium or plutonium or radio, and they also died. Well, of age or cancer. So this is also a mantle which used in a gas lamp, also highly radioactive. There's a problem with the thorium. This is a standard smoke detector. It has a radioactive element in it. What's the difference between this situation and this situation? The difference is uranium is a source of all decays, alpha, beta, gamma. Gamma is very energetic, so don't touch it. So gamma might bring big damage, travels through for long distances. This is beta usually, and beta doesn't travel long distances, and beta easily get absorbed by anything, by plastic. Okay, so to kill gamma, we would need something like this piece of lead. So lead is a good absorber for that. Well, on other materials can do the same thing. Now, reaction. That's going to take a while, but be patient. The uncontrollable chain reaction. Caution, it's dangerous. Can you see what's there? Some do, some don't. It's all about pressing the right button. What do you see? Mousetraps. All charged. Because charging mousetraps is a really, really long process, especially if you make one little mistake. What do we do now? We charge them even more. Each strap represents a stable nucleus. I need to put a neutron in it. I don't want to be killed like physicists. All right. Now you see why physics is dangerous. Well, what? You have to be patient. And now you know why only people with very steady hands can do physics. It's in a state of mind. I can do it. Can I? Stay. By the way, this triggering happened first time in 10 years, just for you. You're lucky it didn't trigger everything, because yesterday it triggered everything. We can cut the tension by the knife, right? The last one. First part was done. Well, it's an explosion. You don't want to kill anybody. So we need a dome, like in Chernobyl. All right, now we need a trigger at that single neutron which excites the first nucleus. Excited? Come on. It worked. That's what uncontrollable chain reaction is. It's dangerous, but it's manageable if you know how to do that right. I need coffee. Now my hand's shaking. So, how can we manage it? Well, we need something to maintain the number of neutrons. Beryllium rods usually do that nicely. So if we don't do that, that's what happens. An explosion. If we can maintain the number of neutrons, we get a working atomic plant. That's it. And we talked about energy in PY105. We know it's inevitable. We will use atomic energy because, well, oil eventually and coal just will be done. Now, we've seen this chart, and this tells us how we can gain even more energy. So from radioactive decay, from spontaneous radioactive decay, there is a certain amount of energy. It's been calculated. But turns out we can gain even more energy if we collide together stable nuclei. In that case, the amount of energy released is much, much larger. This is just one of the examples of the reactions. We call it thermonuclear reactions. And that's what one of the reactions happening in every star in the sun. That's why they're so bright and energetic. So first, those particles, they have to travel so fast because they have to break the electrostatic repulsion barrier. So the temperature should be huge, and gravity does that first. And then when the temperature reaches the, well, high enough values, so those particles get close to each other, close enough to form one excited, very, very unstable nucleus, and decays. And the amount of energy is so large that if we had only 1 mole of the isotope of hydrogen deuterium, 1 mole of it would give us 2 times 10 to the 12 joules of energy. Unfortunately, so far, we cannot manage this reaction. We can only use thermonuclear reaction in the form of uncontrollable reaction. So this is a thermonuclear hydrogen bomb. It has atomic bomb inside to bring the temperature high enough. And several things like that can destroy the Earth like that very easily. So we're lucky we're still here around. Use that time. Well, we have talked about the difference between quantum world and classical world. This is one of the very important differences. In a classical world, if the amount of total energy is lower than the maximum energy of the barrier, classical particle always remain inside. But in a quantum world, we don't know why this happens. We close your eyes and that particle might be outside. That's actually what its decay is. The particle, alpha particle, the first model by George Gamow, the alpha particle inside uranium, but there is a probability to find it outside. We call it a tunneling. Of course, it doesn't drill the hole. Yeah. It's just there. It was here, now it's there, with a certain probability. That's what a decay basically is. And a classical particle, when it hits the barrier, just bounces back. We would have to give an extra kick to this, extra energy in order to bring it over the barrier. The quantum particle, by some reason, we don't know why, might just be tunneled outside, just be there. Well, sometimes in our life, we can also hit a barrier, right? Talk to our friends, boss, teacher, parent. Every time when that happens, ask yourself, what kind of a particle are you? Are you a classical particle, hit the barrier and bounce back? Or are you a quantum particle, which can tunnel through? Think about it. Last question. This is one. That's a long memory test. 6 weeks in PY105, 6 weeks in PY106, every single day. All right. Three. This is an example of a very important psychological phenomenon. We look, but we don't see. We have to guide our attention. Now we're done. Now, my standard disclaimer. So whatever you said yesterday doesn't affect basically anything, because only 2 or 3 people will read it. Well, I always post it online, but who would read that? If you really want to broaden your audience, give an advice to other people, go online, but be specific. Don't just vent out your emotions. Be specific. What would work for you, what wouldn't work for. So just give an advice. If you like or don't like this and that, never take this course. And the second thing I want to say, always, Right now, the whole world is in a phase transition, including America, every country. And no one knows what's going to happen. The new phase is being built. And basically, if you want to ensure that that phase, new phase, will work for you, pay attention to what's happening. Be engaged. Don't trust anybody. Question everybody. And think for yourself. That's it. Now, I'm done. If you have questions, we stay. If you have no questions, we go. And right now, everybody can just, if you don't want to ask a question and don't want to hear the answers, you're free to go. Nothing is left. Yes?
For thin films, for the minimum, when you have delta R equals m minus 1/2 lambda film, technically,
Keep it.
technically, since when you have that pattern, you have two ways to go. You have the screen. Can you go up and you can go like up and down, right?
You mean like this? And you see, when we draw a picture, the picture kind of shows rays traveling toward the eye. But if really destructive interference is happening, the actual picture would look like this. Nothing would, for that particular thickness, for that particular wavelength, and for that particular n, that's it. The real picture would look like this. The person looking from another side would observe that light. This person sees just nothing, black. That's what we say, dark or black.
So the equation should still stand, because I was looking online, and all of the equations that I found were saying I should use m plus 1/2, and I was just confused, because when I used m plus 1/2 versus m minus 1/2,
You would get a different m, but you wouldn't get a different thickness.
okay.
This is a matter of counting. You can start counting from 1, or you can start counting from 2. And eventually, you would get to a certain m, but that m, even if it's different from this m, would give you the same thickness here. You just, you know. And when people use a plus, they start counting from 0. For me, it doesn't make sense, because 0's maximum exists, but 0's minimum doesn't exist. So why would assign a number which doesn't represent any physical phenomenon? So that's why I use a minus, and I start counting from 1. Yes?
There's an equation in the equation sheets under Bohr's model, and it says En minus Em is equal to E photon.
Yes?
What is En and Em?
The nth energy level and the mth. Because in a hydrogen, energy is counted by numbers 1, 2, 3, 4, 5, and n represents a certain level, and m represents a certain level. So the photon should have energy which is equal to the difference between these two energies. And it doesn't matter if the photon excites and the atom and energy increases, or atom loses energy and photon flies away. This is always this, so it's basically negative 13.6 over n squared minus negative 13.6 over m squared for wherever n and m. And the homework has a problem about Paschen series. So this is final for Paschen series, for example. But initial should be, if hydrogen emits light, the initial should be higher, maybe 5 to 3 or 8 to 3. Questions? Yes?
Unless it says, like, specifically, all of the equations for quantum the answers in, like, kilograms or like joules.
No.
Unless it, you have some where it
We,
says, like, you need to put in electron volts or meters, but
no. If you have to solve a problem related to quantum phenomenon, you can use any unit you like, any unit which is convenient, which gives you the answer faster. You just have to write that unit. You can use electron volts, you can use mega electron volts, you can use nanometers, anything. You just need to write it down so people wouldn't confuse your unit with international unit. That's it. Okay.
Bohr's model that says, like,
This is, and Z is an example when, well, D is used for the example when it's not hydrogen, but something else with only one electron. There might be one problem related to that on homework. But you need to remember that wherever element is being used, it's assumed there's only one electron left orbiting it. That's why we can use that equation with Z. We just have to find what Z is equal to according to the name of that element. And use it. That's it. Yeah, if you have questions, please go ahead. Yes.
For lenses, you know how real and virtual is flipped in comparison to mirrors, like for lenses? Does that mean the right side of the lens is positive, or is it still negative?
No. Well, first of all, the general rule for lenses or for mirrors of any kind, real, what it means? It means the eye is positive, for sure. And it also means, if you look at all the diagrams, the real images are inverted. And virtual means the eye will be negative, but the virtual image is upright. It doesn't matter if it's formed by lens or mirror. For a lens, a real image will be on another side, of course. For a mirror, the real image will be on the same side.
Right. I see.
Yeah.
Okay.
Yes.
So why is it that when we talk about like decay, we don't include electrons,
Don't include what?
electrons? Why do we just subtract from the atoms?
No. Physically, you're using a nucleus and another nucleus. That's what physically is happening.
So how does the electrons surrounding it?
Well, the easiest way to heat it up, you heat it up, the electron cloud being stripped off, you just shoot the nucleus. The nucleus is positive, so it has charge. If it has charge, you can accelerate with electric field, You can use magnetic field to aim it at the target, you know. That's it. So the actual reactions, the actual physical reactions which happen there involve nuclei. It probably there is somewhere online a table of nuclear masses. We could be using nuclear masses directly, but it's just easier using atomic masses, but keep in mind that we have to get rid of electron masses from that number.
Yeah. Okay.
You had a question? Okay. See? I helped. Oh, yeah, thank you. Yes?
There's another equation in the Bohr's model that says Rn.
That's the radius.
Radius, okay.
And we
There is, I think, one problem on a homework where you would have to calculate the radius. Yeah, but it's very simple because the radius of the ground state has been calculated. It's a fixed number. You just take that number, multiply by n squared. That gives you the radius of any orbit. Questions, please. Any question? Oh. Keep the ball. All right. Well, thank you very much. So I'm going to go to the 121 because I have office hours soon. So if you have any questions, I'm going to spend there several hours.
When is your office hour end today?
End? I don't remember.
Oh, okay.
I know when they begin, after lecture.
Okay.
And they end when I see a teaching fellow entering the room.
Okay.
I don't need to remember time. Hi. I'm going to take this. Take this, and I'm going to take this down so it wouldn't. Oops. All right, so.
Thank you, Professor.
I was doing a problem in office hours with TF, and we did it multiple ways. And well, he said that he thinks it's correct, but Webb is not exactly correct.
No.
Yeah, that's what I figured because last time he said that, I did it with you and it worked. So
Which problem?
it was part 3, question 3.
Three.
I have my work. Yeah, this one.
No. This is a straightforward problem. I know it's gonna work. And
This is what he did, and then I also have mine.
so, for the electrons, 445. Something with calculations. The strategy is absolutely correct. The only thing is I wouldn't all the numbers, you have to get the same results.
They got the same. For H times C.
I think I had it somewhere on a slide.
Oh yeah, it's only given to us in this way.
So this is H, 6.63. So 2.99.
Joule conversion.
How did you convert it?
I divided by, there was a joule, right here, this joule conversion. Divided by 1.6 times 10 back into.
Well, but what I did just the same, and I got 2.78, exactly the same number I have here.
Okay, 2.78, yeah, I had 2.79, so maybe.
Well, for the Weber sign, 2.78 and 2.79 actually
Might be different.
may make some difference